everyone, in this video we're going to look at independent events. So here's our definition. Events A and B are called independent if, and here's our probability notation, the conditional probability of A given B is just equal to the probability of A. So what this is saying is that this condition, the given B portion here, this doesn't make any difference. So whether or not B happens or doesn't, it has no effect on the probability of A. So here's an example. If we draw two cards from a deck of cards without replacing them, I'm looking at the two events that the first card is an ace and a second card is an ace. And to make this make a little bit more sense, I'm going to call event A that the second card is an ace and event B that the first card is an ace. So I want to think about what would the probabilities be, both of just the probability of A on its own and then the probability of A given B. So the probability that any card that we choose at random from a deck of cards is an ace is the number of aces out of the total number of cards. For a standard deck, that would be 4 aces out of 52 possible cards. So if I'm just looking at event A on its own, it doesn't really matter that this is the second card. If I don't know anything about what the first card was, I'm just looking at the number of possible aces out of the total. In contrast, if I look at the probability of A given B, this is the probability that assuming event B has already happened, so we drew a first card and it was an ace, then what is the probability that the second card is an ace? Well, the probability is a little bit different now because by removing a card from the deck, we've changed the options. So there are fewer cards now. Instead of a total of 52, there are only 51. And because the first card was an ace, there's fewer aces as well. So the probability is 3 out of 51 rather than 4 out of 52. In this case, this is a fairly significant change in probability. The probability of A given B is a fair amount smaller than the probability of just A. So are these events independent? No, they're not. These probabilities are not equal. And what we would say here is that in this case, whatever you get for that first card draw is going to affect the probability of what you get on the second card draw. This is true in general, not just about these events with aces. So we would say that these are dependent events. Now I want to compare this to a slightly different scenario with almost the same events. So here I have the same events, second card is an ace and first card is an ace, but instead of drawing these cards without replacement, I'm going to draw the first card, put it back in the deck, reshuffle, and then draw the second. So in this case, if I compare the probability of A with the probability of A given B, so probability of A, just the probability that the second card is an ace, this is the same as what we saw before. The context doesn't really change. This would be 4 out of 52. The probability of A given B, so now again, I'm assuming that B has already happened. So the first card we drew was an ace. But if I take that ace and then put it back into the deck and reshuffle it, the probabilities for the second card are still exactly the same. This probability would still just be 4 out of 52 because there's still 4 cards. There's still an equal chance of any of those cards happening because we reshuffled, and there are still 4 aces. So in this case, it's true that the probability of A given B is equal to the probability of A. So are these independent? Yes. Here's kind of a less obvious example. I have two events. Event A is you bring an umbrella to school today, and event B is it rains today. I want to know if these events are independent. I want to be thinking about the conditional probabilities involved here. There's actually two different equations I could look at. I could look at probability of A given B equals probability of A, or probability of B given A equals probability of B. Either one of these can be conditions for independence. It doesn't really matter which event is A versus B, but sometimes one of these is easier to think about than the other. So here we have to think a little bit about the context. I don't have exact numbers. I don't know what the probability that it rains today would be. It depends on what day it is, of course. And I also don't know what the probability of you or I bringing an umbrella to school today is, because that depends on lots of different things. But let's just think of a scenario where, I wake up in the morning, I look outside, it looks really cloudy, or maybe I check the weather app on my phone and there's a 30% chance of rain. I might be more likely to bring an umbrella. Let's think about just the probability of B. So the probability that it rains today, again, it's going to depend on the day, but let's just think about a day where maybe it's forecast 30% chance of rain or something like that. There's some probability that it rains. If I compare that to what's the probability that it rains given that I brought an umbrella today? Well, if I brought an umbrella because it looked particularly cloudy in the morning, or maybe because I checked my weather app and it said 30% chance of rain, then it's really more likely that the rain is going to happen on that day. If I know that this was a day that I brought an umbrella, then the chances of there being rain are higher. And this is not because me bringing an umbrella makes rain more likely, right? I don't have any causal effect on the weather, but the condition that I brought an umbrella to school means that that day is more likely to be a rainy day versus just a generic day. So that would indicate that assuming that my bringing an umbrella was based on some kind of evidence that there might be rain, that these probabilities wouldn't be the same. The probability of B given A would be a little bigger than the probability of B. In contrast, if I look at the other order, the probability of A, so the probability that I bring an umbrella to school on just any day, versus the probability that I bring an umbrella to school given that it rains today. This conditional probability feels a little strange because me bringing an umbrella to school likely happens before the raining. So the condition here feels a little bit backwards. But given that this is a day on which it rains, there's a greater chance that that's a day that I brought my umbrella. Now, I can't predict the future. I don't know whether it's going to rain or not on a given day, but there's a higher chance, again, this probability of A given B would be bigger than the probability of A. In other words, big picture, the events that I bring an umbrella versus it raining are not completely independent. I'm not just randomly deciding whether to bring an umbrella or not. If you woke up every morning and flipped a coin, and if it was heads, you brought an umbrella, and tails, you didn't, then these would be independent. Or another example, if you always bring an umbrella to school, you just, keep it in your bag or something like that, then these events would be independent as well, because it doesn't matter whether there was rain today or not. The probability of event A would always just be 100% or 1. But these are not independent events under kind of typical conditions, because one happening might affect or it might be linked to the different probability of the other happening. This is a particularly tricky example, but I just wanted to include this to emphasize that it's not, one event prevents the other or one event guarantees the other necessarily. It's just that the probabilities are different when you have the information about one of the events versus if you didn't. The independent versus dependent case that we see a lot of in statistics involves sampling with or without replacement. So I have a scenario here. Suppose we're sampling 2 students from all of the Red Rocks Community College students and looking at whether each student is graduating this year. So I have 2 events. I have the first student graduating and second student graduating. Are these independent? So just like with the cards example, if we are sampling the first student and then sort of returning them back to the pool of students and then sampling the second student, then these will be independent events because it doesn't matter whether the first student was graduating or not. That's not going to affect the probability of the second student. But if we select them without replacement, then there is actually a slight difference in probability. So in general, if you select with replacement, like putting your card back in the deck and shuffling, then your repeated selections will be independent. But if you select without replacement, they are dependent. So if I'm considering the probability of the second student graduating, I don't know what that would be. Let's say that there's 400 graduates out of a total of 10,000. I'm just making up these numbers because I don't have them with me. If we assume that the first student we selected was someone who was graduating, and we didn't replace them before we selected the second student, that would mean that the remaining students was, instead of 10,000, 9,999, and the remaining students who were graduating would be 399. These probabilities are slightly different. By not returning the first student that I selected to the pool, I slightly affect the probability of the second student, in this case, graduating. And this is pretty typical for selections. If you're making multiple selections, whether it's 2 or 3 or 4 or whatever, selecting with replacement will always be independent. Selecting without replacement will be dependent. And when you do sampling, you usually are selecting without replacement because we're typically just selecting a group of people and not kind of selecting one, returning it, mixing everyone back together, and then reselecting. However, in this case, we did select without replacement, or likely did, but because we're selecting from such a large group, if I think about these different probabilities, 400 out of 10,000 and 399 out of 9,999, these probabilities aren't the same, but they're practically the same. They're extremely close together because I'm not really affecting the pool or the probability of my second selection much. So in this case where we selected without replacement from a large group, we will often kind of treat these as independent. They are technically dependent, but because that change in probability is so small, we can kind of simplify our calculations, and we'll see this in the next section with calculating and probabilities. We can kind of treat them as independent. They're sort of close enough to independent. And this is just a general rule of thumb. You want to be selecting a relatively small number from a quite large group. Finally, why do we care about independence? Events being independent is a central assumption of many important probability distributions that you'll see in the next chapter. And it also affects our calculations of AND events, or compound AND or intersection events, using the multiplication rule. That is in the next video in this playlist, so you can check that out and see how independence affects those calculations. That's it for this video. Thank you for watching.